Hello everyone, my name is Zheng Pan, a PhD student at Monash University. In this video, I will introduce our CVPR paper, Stitchable neural networks. Today we have thousands of pre-trained models in ModelZone, but each model has a fixed computational graph. In reality, we need to deploy models to diverse platforms. So in this paper, our goal is to utilize these pre-trained models to cover many flop accuracy trade-offs. So given a pre-trained model family, our method inserts a few stitching layers between these models. So in this case, we can cheaply produce many new networks with a few epochs of fine-tuning. So for example, by stitching DIT models, we smoothly interpolate the performance between anchors. And furthermore, by stitching swing transformer, a single SNNet can challenge hundreds of pre-trained models in TRMM ModelZone. So we begin with introducing the concept of model family, as it is the foundation of SNNet. So model family means pre-trained models with functionally similar architectures, but with different scales, such as DIT tiny, small, and base, and resonant 18, 50, and 101. So the difference is usually in the depth and width. So based on the model family, our work is further inspired from model stitching. So specifically, previous works have found that the same architecture trained with different random seeds can be stitched together without significant performance drop. And even with different architectures, they can also be stitched. So by stitching, we refer to connect two networks with a simple stitching layer. And because the two networks are pre-trained, to obtain the stitching layer requires a simple least square solution by finding the right mapping between feature maps A and B. So A is the output from the first portion of the network, and B is the input to the last portion of networks. Now, given the different anchors, we have two choices for stitching. One is fast to slow and another is slow to fast. In this work, we adopt the first strategy as this aligns with existing network design, means we increase the channel dimension when the network goes deeper. And besides, we empirically find fast to slow achieves a smoother flop accuracy curves in our experiments. We also proposed a nearest stitching strategy, which limits the stitching between two anchors of the nearest model complexity and performance, such as finger A and B, but it excludes the stitching anchors with a larger complexity and performance gap, such as D, C, and D. Furthermore, since different anchors can have different network depths, we propose two methods for stitching. One is paired stitching for stitching models with equal depths, and another is unpaired stitching for models with unequal depth. But the general idea is to stitch blocks as sliding windows, so it can cover all blocks or layers in a neural network. So finally, training stitchable neural network is surprisingly simple. At each training iteration, we randomly sample stitch from a predefined configuration set. Then we just train the stitch as a normal network with gradient descent. So based on the DIT model family, we compare the SNNet with individually trained networks. As the table shows, a single SNNet can cover a wide range of performance and efficiency trade-offs. And to be emphasized, it saves the most 22 times local storage and computational cost when comparing with training these individual networks. And moreover, SNNet also works with stitching convolutional neural networks and even mixing CNNs and VITs. So for example, in figure 7 left, we successfully stitched resonant 18 and resonant 50. And on the right, we show that stitching resonant and swing transformer can also achieve good performance as well. We also study the effect of different stitching directions. As this figure shows, comparing with slow to fast, we found fast to slow will generally produce a much better performance curve. So by default, we'll choose fast to slow in SNNet. We have also studied the effect of least square initialization. In general, we found that at the initialization phase, least square initialization can help to find some good stitches, and after training, it also helps to improve the overall performance curve. In Finger B, we explore the effect of near-race stitching. So by default in SNet, we enable the tiny small stitch and small base stitch, but we exclude tiny base and sequentially stitching such as the tiny small base. And in general, we find by comparing tiny base to tiny small and small base, we find stitching anchors with a large performance gap in complexity can achieve inferior performance. And moreover, we can also compare foley fine-tuning with training the stitching layers only. But overall, we find foley fine-tuning is much better. And if we only fine-tuning the stitching layers, for some stitches, it achieves much worse performance. So last, we would like to mention that SNet has some limitations. So for example, in this paper, we mainly study the tasks on computer vision, basically the ImageNet 1K, but we do not explore the settings in natural language processing tasks, and we also do not explore the transfer learning and dense predictions, but we believe this can be studied in future work. And besides, future works may also consider improve the training strategy as well, because in the current training strategy, we randomly sample a stitch in a predefined configuration set, but if the space is enlarged, some stitches may be trained insufficiently. So in that case, we believe the training strategy can be improved in future work. So thanks for listening. That will be all for this presentation. And if you are interested in more details, please feel free to scan the QR code on the left to find our papers on arXiv. And you can also scan the QR code on the right to find our project page. And we have also released the code on GitHub. So thanks for listening.